Hello and welcome to the AI Research Roundup. I'm your host, Alex. Today, May 9th, 2025, we're looking at an ICLR conference paper published a bit over 3 months ago, a probabilistic perspective on unlearning and alignment for large language models. This paper argues that just checking one best answer from large language models, often via greedy decoding, where the model picks the most likely next word, isn't enough. Especially for tricky areas like unlearning, that's making models forget things, or alignment, ensuring they're safe. So the authors propose a probabilistic way to test them, by looking at many possible answers to better see the risks. So this first figure really sets the stage. It shows a large language model that's supposedly unlearned or made to forget who Harry Potter's best friends are. On the left, you see the deterministic approach using greedy decoding, where the model picks the single answer based on the highest token probabilities. That's the likelihood of each word. Here, no information leak is detected. But on the right, using the probabilistic method by sampling multiple answers, one of these samples clearly reveals Ron and Hermione, showing a leak. This really drives home how single answers can be misleading. Building on that, this next set of charts illustrates a proposed solution called entropy optimization. Entropy, in this context, measures the predictability or certainty of the model's answers, so low entropy means high certainty. Panel 1 shows the starting model confidently identifying Harry's friends. Then, Panel 3 demonstrates that after applying their novel unlearning method, the model becomes very certain about a different answer, John, effectively suppressing the original. Importantly, Panel 4 shows the model retains its certainty for information it's supposed to keep, like correctly identifying the capital of Canada. This selective adjustment of certainty helps reduce information leakage. Alright, so this next figure really drives home why these probabilistic checks are so vital. Panel A uses a binary leakage bound, or MBN. That's a measure of how likely specific information is to leak. For the Harry Potter questions, greedy decoding suggests no leak, but the probabilistic MBN reveals a significant chance. Panels B and C then look at Rougeil scores, a common way to measure text similarity, on a benchmark called TOEFL. These and subsequent panels compare their proposed unlearning algorithm against others, like negative preference optimization, or NPO, consistently showing their method better reduces this probabilistic leakage. Okay, so this table 1, really lays out these comparisons on that TOEFL dataset we were just discussing. It lines up several unlearning methods, including negative preference optimization, against the author's own. Looking at the deterministic Rougeil scores, again, lower means better unlearning. Their method scores best at 0.20. But the crucial insight comes from their probabilistic expectation deviation score, or ED score. Here, their method also achieves the lowest mean leakage. But importantly, the standard deviation, which measures the consistency of unlearning, drops to 0. This near zero standard deviation demonstrates their approach more reliably prevents probabilistic information leaks. So moving on, Figure 5 presents some ablation studies. These are basically experiments where you tweak different parts of the system to see what happens for their proposed entropy optimization. Panel A shows that by carefully adjusting a parameter for retained regularization, they can maintain output diversity. That's the variety in the model's answers. Then, Panel B illustrates how token confidence, or how sure the model is about each word, increases for the information it's supposed to forget, while staying steady for things to remember over training epochs. Finally, Panel C plots the expectation deviation score against model utility, suggesting the model's general usefulness isn't strongly tied to the specific strength of this entropy regularization. So, shifting from unlearning, Figure 6 looks at model alignment. That's ensuring models behave safely, using the jailbreak bench dataset, which tests for toxic outputs. For models like Phi and Vicuna, the top plots show average toxicity from many samples. The black line in the orange area is higher than the single greedy result, the blue line. The bottom bar charts, using the binary leakage bound, MBN, then show probabilistic checks, the orange bars, find more toxic responses than greedy methods, the blue bars. This really highlights how single answers can hide potential problems. Okay, so in conclusion, what we've seen is that relying on deterministic evaluations, like just taking the single most probable answer via greedy decoding, can hide significant risks in large language models, especially for unlearning and alignment. This work strongly argues for and shows the need for probabilistic evaluations, essentially looking at the model's entire range of possible answers by sampling to get a truer picture. They've also given us new tools for this. That's all for this AI Research Roundup. I'm Alex. Thanks for listening.